Okay, welcome back, everybody. All right, so this is where I left off, talking about, as a very simple example, something that looks like Namecoin in Ethereum. Somebody told me at the break that, which not too surprising, that this has been done, I guess, in a much more serious way, probably multiple times, I'm sure, but I guess there's a project called ENS, which is an attempt to do this. So if you want to see, I guess, a much more robust version of this, you can find the code online, certainly. Okay, but so to sort of recap where we were, so hopefully there's kind of a mental understanding now of how this contract gets uploaded to, included in the blockchain, how you could write this code, compile it, obviously. You create a new contract with this address. It would then have its storage and balance and everything else. You could sort of pay to include this in a transaction to include this new contract. And if you pay enough, obviously, and wait, miners will include it in the blockchain. And then as these functions are getting called, so keep in mind that anybody in the world can call your contract or cause it to start executing some code. If you don't want anybody to be able to call it, you would do some checks to basically reject calls from people that you don't know about or aren't in some certain list. But essentially, anybody, once you've created this contract, can create transactions, calling code on it, which will update its state, potentially change its balance, everything else. Broadcast them on the network. Miners will include them in the blockchain. Miners will track the state of this contract, and it will sort of live on the blockchain. And so especially if you haven't worked with Ethereum too much before, I think this can be a conceptual stumbling block. People say, who runs this code? Which computer is it on? Where is the storage? And again, the answer is that any miner in the system, or really any full node that's verifying the full Ethereum blockchain, will have a copy of your code, and they'll have a copy of the storage of your code, and every time there's a transaction calling it, every one of those full nodes in the world will have to repeat the computation, so they'll interpret your code and update its state and all the rest of it. So when we say it lives on the blockchain, obviously the blockchain is sort of an abstraction. What that really means is that everybody who's tracking the blockchain will be tracking your code and running every transaction that calls it. But it doesn't live on your computer or really any specific computer. It's maintained by consensus as part of the blockchain. Okay, so if that notion, and again, it's a little bit strange. It's a little bit of an electron being everywhere and nowhere type of thing that's not very intuitive. But so your contract is kind of everywhere in every one of these nodes at once. But if that makes sense, we can start thinking a little bit more about this language here. I didn't even say which language this code is written in so far. How it's actually compiled and interpreted, how memory is laid out, stuff like that. So I'll jump a little bit more into the actual programming aspects here. So like I said, I hadn't said previously, but this example is written in a language called Solidity, which is what I'll be talking more about. There are other examples. You can basically write any high-level language you want for Ethereum, but the most popular one by far is called Solidity. And it compiles down to something called EVM, or Ethereum Virtual Machine Bytecode. So the actual fixed language designed by the system is EVM. Solidity is really sort of a higher level abstraction on top of it that compiles down to EVM. So if you read the Ethereum specification, which I think is actually quite nicely written and readable, if you want to find it online, you search for yellow paper. That actually defines this EVM language plus other things about the Ethereum blockchain. Okay, so I'll tell you a little bit more about this Ethereum virtual machine. And remember, this is where the code always runs. So if you look on the Ethereum blockchain, The only thing that's included in the blockchain is EVM bytecode. So you don't, in practice, you can often find the Solidity because there are some nice websites that trawl GitHub and sort of compile the code there and match it with contracts on the blockchain. But if you're just looking at the raw blockchain, this is all you'll see is EVM code. So in some ways, it's actually quite similar to Bitcoin script. There's a stack. You have a lot of data for instructions for pushing and pulling data from the stack. You have sort of basic arithmetic. And like Bitcoin, there's special operations that do some crypto operations. So there's sort of some crypto built-ins that you get for free, basically. If you want to do a SHA-3 hash, you don't have to write it. That's built into the virtual machine. The big difference between EVM and Bitcoin script that's really sort of the root of all the changes in the system is the fact that you'll see there are some jumps here, so you can actually loop. So unlike Bitcoin, where the whole point was that the code is interpreted in one pass, this is now more of a programming language you're used to that can loop. It can infinite loop, of course, if it can loop. But it still has this built-in stack like in Bitcoin. The other thing is that your code has this big storage space to work with. So you have to really emphasize big here. The theoretical amount of space that your code has to write to is really, really huge in Ethereum. So basically, every 256-bit value is an address in memory, which stores 256-bit words. So the word size is very big on this machine, and the memory space is just unbelievably big. So you basically get this huge, huge storage space. And storage is persistent, so it's kept sort of forever. You can run a transaction that edits storage, and it will be there the next time your contract runs. You also have basically the same amount of space, which is called memory, and the only difference there is that the memory is volatile, so every time you run a new transaction, you wipe away, you start with a blank slate in terms of memory. So you can represent some theoretically incredibly, incredibly big amount of space, but before you get too excited about how much space you have to work with, it's really, really expensive, so in practice, you're going to use very little of it. But in theory, you have this massive amount of space. Like I said, don't plan to use all that space because you won't be able to afford it, but in theory, it's there. There's some other features that are built into EVM. So you can do some introspection about the state of the blockchain at the time that you're running. You can sort of ask which block number I'm in. Someone asked about time, so you can query the timestamp of the most recent block. You can even load info about who mined the block. You can sort of look at your gas budget. I'll talk more about gas in a minute, but that's basically how much budget you have to perform computation. So you can sort of see, maybe if you're running low on gas, you can try to wrap up what you're doing and finish. And then you have all the info about who called you, who caused this code to be running, did they send money, et cetera. And the output, so this is what your contract can actually do that's useful. Well, you can write to logs. That's actually not very useful. It's really just sort of for debugging or informational purposes, but doesn't really cause anything to happen besides some data being written out. What's actually meaningful that you can do is send messages to other contracts. And the reason that's meaningful because you can cause other contracts to run some code, or you can send them money. Or I guess you can do both at the same time if you want. But essentially, that's really the only meaningful action that your contracts can take that will really incentivize things to happen or not happen is that you can send money. You can also self-destruct, which just means you can sort of terminate and say, this contract has served its purpose and doesn't need to exist anymore, and you can cause it to be removed from the system, which is kind of a polite action to take when you're actually finished. So I think there's a lot of subtleties I could go over here. I know Vitalik is going to talk later about pitfalls, so most of this will probably come up again. I guess this is just a little foreshadowing. There's some built-in things like the number of calls between contracts that can happen, and interesting things happen when you get near the limit. I think I'll leave it there, and I'm sure Vitalik will say more about some of these sort of interesting edge cases in EVM. OK, so the question you may be asking, especially if you haven't seen Ethereum before, how is it possible for your contract to have this 264, or sorry, 2 to the 264 bits of memory? Obviously, that's way more memory than exists in the world or could ever exist. So how is it possible that that's actually stored for each contract, no less, in Ethereum? The trick is that a really nice, efficient data structure is used to store it. And the efficiency really is that all of the memory space that's set to 0, you don't store, you compress. You really only store the non-zero bits, and that lets you get away with having this theoretically huge amount of space, but storing it in a very compact way because you're only storing the interesting non-zero parts. So, as I said, it's basically a map from 256-bit values to 256-bit values. Not surprisingly, you use a tree to actually represent this. If you just used a simple Merkle tree, like Bitcoin uses to store transactions, this thing wouldn't work because there's 2 to the 256 words of memory. So if you tried to just build a Merkle tree committing to that huge memory space, you'd never be able to finish. It's really, really big. So you can notice right away, though, that since most of this memory space is empty, you don't have to sort of keep computing all of these empty subtrees in your Merkle tree. So you can compress all those, and then it becomes sort of tractable. That's kind of the core of the trick. And then there's kind of a second thing, too, which is that even for the words of memory that are written to, you sort of compress them, and you only build the tree deep enough to represent the words that are actually non-zero. So I know I went over this a little bit quickly. It's really tedious to actually go through all the details of how this tree is built. But just to give you the intuition, you're building a tree very much like Merkle trees, which you've probably come across in other cryptocurrencies, in Bitcoin or other applications. But you're really just sort of taking all the 0 bits of this tree. So imagine that obviously instead of just 8 words of memory here, you have 2 to the 256 words of memory, and only 4 of them are written. There's just some nice tricks where you compress this all down into a very small tree. And that's what Ethereum does, and that's how you can get away with having this theoretically really big space and produce commitments to it that are quite small. So if you want to read more about the details of that, pretty important, I think, for understanding Ethereum, because this is, actually the same data structure is used in 2 places. It's used both to store the map between addresses and what, the code and the balance and the state and everything for each address. And also within each address, it's used to store the storage for that address. There's kind of a few subtle quirks of how this is actually done in Ethereum. So if you search for Merkle Patricia tree, you'll find a lot of documentation and code, et cetera, about how Ethereum actually builds this. And you may be thinking, I've seen this data structure before. It turns out there are a whole bunch of different names that have been used at different times by different people. I see Vitalik smiling at that. So yeah, it's sometimes called a radix tree. It's sometimes called a prefix tree. Lots and lots of different ways of describing this. Partly because it's such a really beautiful data structure. that a lot of people have used it for different things over the years. OK. So I said I was going to talk about gas. So the joke that it works for European students, not as well for American students. Running code on Ethereum is like Ryanair. You sort of pay to start, and then everything you want to do, you have to keep paying for. Did anybody actually fly Ryanair to get here? Oh, okay. I actually don't know if Ryanair flies to Israel. They do? OK. How many people have flown Ryanair in their life? OK. I was a student in the UK. I flew Ryanair all the time. So I got very, very good at avoiding paying fees on Ryanair. With Ethereum, there's basically no avoiding it. You have to pay gas no matter what you want to do. But it's kind of a necessary evil. So obviously, it's unfortunate that you have to pay for computation. But this is the only way to incentivize people not to just run programs that take a really long time or use a lot of storage or other things that are expensive for the system. And remember that the miners, every miner has to run all of your code and keep all of your storage around. So it's really important to give people an incentive not to use too much. And the other thing, of course, is that this makes the halting problem go away. You can't have an infinite loop in Ethereum in practice because you run out of gas eventually, and then when you run out of gas, your program's going to halt no matter what. So kind of at the low level, while the Ethereum virtual machine is running, every step that the virtual machine takes, there's a cost associated with it. And you basically start with an amount of gas at the beginning. And every step the thing takes, your amount of gas remaining goes down until eventually either the program finishes or you run out of gas, and then that will cause your program to finish. And the prices obviously vary on what you're doing. So the basic stuff is usually a few gas, and it's a little bit more expensive to, say, do a divide instruction than to do an add instruction. But for the most part, most of the basic instructions are pretty simple and cheap. Where you really pay kind of through the nose is for storage. So every word that you want to store, you pay a big fee. In particular, when it's a new word that was previously 0, that's where you really pay, because that's sort of making the tree representing your storage state get bigger. But you'll notice also that there are some instructions here with negative cost. So in particular, when you free memory, you get some gas back. And the reason for that, of course, is that you want an incentive for people to free memory, because then that decreases the amount of state the miners keep around. And if you self-destruct your contract when you're done, you get some gas back, which is nice. So there are some things you can do that cause your meter basically to run backward. But there's kind of no free lunch here. So the way this is interpreted, you'll never get money back from the system. So the best case is that your total gas cost for the transaction can be 0, but it can never be negative. So you can never make money by running some transaction that has all instructions with negative cost. So the system doesn't allow that. The best you can do is run a transaction for free if it's some 0 or less than 0 amount of gas that you consume. So as a result, the full algorithm for metering how much gas your program uses while it's running, it's a little involved. In particular, when you start a transaction, you actually specify 2 things. One is start gas is how much gas you actually want to set aside for this program to have. And then gas price, this is basically what you're bidding to pay for each unit of that gas. So you basically can say, I want to run this code with 1,000 gas, and I'm willing to pay this 5 Wei or whatever your price is per unit of gas. And gas price is basically what the miners will use to decide whose transactions get to run. The miners get to be selfish, and they can favor transactions paying the highest price for gas. So that's kind of set by the market. And start gas is basically how much you're willing to set aside for gas. And then there's a bunch of rules. You have to actually have as much gas. The maximum amount of gas that you're willing to use for your program, you have to have up front. So people always want to ask when they're first exposed to Ethereum, can my contract somehow self-fuel? Can it pay for its own gas out of its balance? And turns out the answer is no. You have to have all the gas that that the program could potentially use. You have to have it, and you have to set it aside up front. And if you don't use it all, you get a refund back. But it's not possible to do anything fancy or like have the contract pay for its own gas. And there are some pretty good reasons for that. I guess we can chat offline if you want to know the design history there. Okay, so what happens when you run out of gas? So your transaction's still valid even if it runs out of gas. It can still be mined and included in the blockchain. But no changes will be made to the state of the system, except that the gas you used you don't get back. So basically, if you sign a transaction that causes some contract to run but runs out of gas, that gets included in the blockchain. The state doesn't change, except that you lose the gas that you paid for this sort of failed attempt to do something interesting. So you don't want to run out of gas. In general, it's something you should be able to avoid, because before you post a transaction, you can always sort of simulate locally and see what the result of your transaction is going to be. But you're never 100% sure, because you can't predict. You have to post the transaction and wait for a miner to include it. And you can't predict fully the context in which your transaction is going to run. So it's possible by the time it actually gets included in the blockchain, for whatever reason, the state of the world has changed, and then you cause a gas exception. But I guess that's really the key thing, is that if you run out of gas, everything is sort of frozen and rewound to where it was before you started. And this can happen in sort of interesting ways when contracts call other contracts. So basically, if you call contract A and it calls contract B and it calls contract C, et cetera, each of these contracts can sort of decide how much gas to pass on to the next contract to run. And if, say, like contract C runs out of gas at the end of the chain here, contract C won't have been able to have any effect. So anything contract C tried to do will be undone. But contracts B and A can recover and actually cause some changes to happen. So in terms of kind of dollar values, I guess I didn't do shekel values, but here are dollar values for you. It's actually gone down, which has been good. It's previously it's been higher than this. But basically you can see most basic operations are really, really small, like fractions of a penny. They do add up if you're trying to do a lot of stuff. And the expensive things are like writing to storage is still more on the order of pennies, if you're dealing in dollars. So yeah, if sometimes when people first hear about Ethereum, they have this idea that it's going to replace EC2, it's going to be their new cloud computing platform. It's definitely not that. So by the time you try to do like a matrix multiplication, you'll be paying many, many dollars for it to run slowly, and it's sort of crazy for that application. The goal of Ethereum is really sort of to express and validate contract logic. So ideally, you're not doing any really big computations or using lots and lots of storage. But if you are, you'll pay for it, and that's what will limit you. Okay, so I think I'd mentioned that you specify the gas price, how much you're willing to pay, and then miners can choose, do I want to actually run your transaction or not? And different opcodes have different prices, which is, the design is supposed to make the miners sort of neutral to what your contract is actually doing. In practice, of course, the miners can discriminate however they want. So they might say, well, the gas price is really high, but you're running a lot of opcodes that I think are actually expensive for me to do, so I don't want to run your transaction. That's fine. The miners can sort of do that if they want. And the equivalent of like what would be the block size debate in Ethereum, how much gas can there be per block? I mean, knock on wood that it doesn't rear its head in Ethereum world as well, but there is a mechanism built into Ethereum to change the gas limit over time. So hopefully, there's not a mortal split in the community over lots of gas or less gas per block. OK. So now I want to introduce you to Solidity, which is the programming language I mentioned, and I think Vitalik will show some more examples of. So if you look at Solidity, it'll look sort of familiar. The code maybe looks like C or JavaScript. You saw it with the Namecoin example. It's maybe a little bit simpler. There's no floating point, and a couple other things are missing that you might be used to. I think the most interesting thing about Solidity that gets used a lot and is kind of very Ethereum specific is that there's this mapping type, which gives you sort of a mapping from keys to values. So it's like a dict in Python or things that exist elsewhere, except the implementation is, I think, really interesting in Solidity and sort of shows what's unique about Ethereum, I guess. So suppose in your Solidity code, you declare you have some map from strings to integers, and this sort of represents values for different people in your system. Pretty common thing to do. Maybe you have sort of 3 users, and they each have some balance. By the way, this is one of the most common things that actually gets done in smart contracts now is that this contract have their own notion of tokens, and people can buy and sell. And people use them for ICOs to raise money and all the rest of it. But anyway, so this is a very common thing. You just want to map each of these users to a balance. The way this actually gets implemented under the hood by your Solidity compiler, you hash the key and also sort of the syntactic name of your map. And that gives you a random location in memory. And that's where you write the value. And similarly, you do this for all the other keys that exist. So there's sort of no effort to exploit locality here, because there's no efficiency from locality of memory. So you sort of spread this mapping all over memory, but that gives you a really cheap way to build this data structure using sort of this huge storage space that you have. So very, very unusual. I think I hadn't seen an implementation of a mapping like this until looking at Solidity or Ethereum. And there's kind of a bunch of implications of this. You can't actually query and see what keys exist. You can't delete the thing. Anything that doesn't exist is just mapped to 0, et cetera. So there's a lot of kind of gotchas to a seemingly simple construction here. OK, so generally, in your contracts, you usually start whenever a code is called by sort of seeing who called me, are they allowed to, et cetera. Is this a valid thing to be doing? And there's this nice, well, I think throw has actually been replaced by a couple of other things now, but this is the old way to do it. But basically, it's very, very common to cause an exception to happen, to cause the machine to halt and everything to undo if there's sort of any problem. So like if someone calls your code in a way and they're not supposed to, or they're not authorized, the default is always just to throw an error, and then that sort of guarantees that you'll go back to where you were before, and the system will keep working. I guess that should say today instead of tomorrow, but there's a lot of subtleties here, which I'll leave, I suppose, for Vitalik to talk about. And I guess I'll say that this, the Solidity EVM as a platform for expressing smart contracts, not necessarily limited to Ethereum. There's kind of a project to use it for other other systems. So you could have a completely separate blockchain, maybe a different consensus layer, maybe it's a permission blockchain, whatever. You could still use EVM and Solidity and all these other tools that are being developed to express smart contracts in some other system. So in particular, not specific to Ethereum at all, really. EVM sort of built for Ethereum, but you could sort of pull that out and use it for another system if you wanted to. And of course, if you don't like Solidity, you can write something else. Especially, anybody in the room who's a student, I think this is a really great PhD level project to write a better smart contract programming language than Solidity, one that's much easier to reason about, to write things without bugs, et cetera. You can sort of do whatever you want as long as it compiles to EVM. You can instantly post it to the blockchain and do cool stuff with it. So just a few words about the Ethereum project. I don't know what the verb is. Ethereum is blank by the Ethereum Foundation. Sometimes people say it's owned or managed or run. It's not really clear what the right way to express the relationship is. But the Ethereum Foundation is like the main real-world organization that has some stewardship, I guess I'll say here. They produce software to the client to actually track the blockchain, et cetera. There are others, so there's basically almost everything Ethereum Foundation does. There's sort of somebody else doing it too, but they're kind of the big player in the space. If you use to the Bitcoin blockchain, just some of the constants change in Ethereum. In particular, the blockchain is much, much faster. So blocks in Ethereum just happen way more often than Bitcoin. And kind of unlike Bitcoin, where at least until recently, hard forks in the system were something that the goal was to have them not happen ever. There's plans to have a few future releases of Ethereum with new features, and there are going to be hard forks, and that's kind of a planned situation. If you are obsessive about tracking the price, you probably know this already, but the price of Ethereum, the value of the whole system, has been kind of slowly gaining on Bitcoin. I think the actual value doesn't matter so much now, but it's like same order of magnitude now as Bitcoin, so the project's been doing pretty well. Of course, it's been going up and down. I like this ETH roller coaster, which gives you a little animation based on what the market is doing of a roller coaster going up and down. OK, so I think I have a minute left, and then I'm supposed to take questions. But I think I'll take 1 or 2 minutes here and just lay out what I think are the most interesting research challenges, some of which will be talked about more. I can go through them pretty fast. But this is basically my attempt to say if you're a student or if you're doing a startup or whatever, these are like the problems I wish that a lot of people, I think, in the community wish we could solve. So one is privacy. I think I don't need to say too much more about that, except that everything in Ethereum is public by default. So doing things where there's privacy concerns, you have to think maybe differently about. And I think there's going to be a whole day of talks about privacy, some including smart contracts, so you'll see more, but big problem. Making sure that everybody has a consistent interpretation of what EVM means, can track the blockchain and apply every input consistently. I think this is a big goal. So sort of verifying that everybody's interpretation of the Ethereum spec is the same. That's a really, really great project to be working on. And similarly, actually verifying that people's Ethereum smart contracts do what the designers intended. So very, very hard to spot bugs, like in the case of the DAO that are sort of buried in code. So in addition to maybe making a better programming language, sort of having a way to verify that these programs have some properties we want. Scaling, so this question was asked already, but yes, indeed, scaling is a really difficult problem. There's various different ways that have been proposed to shard the system, which means different miners only track part of the system, not the whole thing. That would potentially allow a lot more scaling. The problem with sharding is that you can't really tell when a transaction is uploaded which other contracts it's going to interact with, which parts of the global state it's going to touch. That's sort of an inherent part of the fact that this language is universal. You don't know what the code's going to do. So the details of how these sharding proposals work get really complicated really fast, but this is like a really important problem to solve. And the last one I was going to say is, switching to proof of stake. We have a whole talk about that. I'll just say, the best way I think to dive in if you want to learn more, besides, I guess everybody here is here this week, so that's a great way to learn more. Go to a blockchain explorer. So there's websites that will sort of show you the blockchain and what's happening. I think Etherscan is nice, but there's Ethplorer, there's others. You can look at the blockchain. You can see which transactions are being included. You can look at different contracts and what's there. And I think that's a great sort of next step if you're new to Ethereum to get a working sense of how all these pieces fit together. And yeah, with that, a few more minutes for questions.
Let's thank the speaker.